All right, guys, we're going to continue our discussion in regards to electrochemistry, right? We're talking about in a voltaic cell, guys. This is what the proper name is, but if you guys just think about it as batteries, so we're going to learn kind of how batteries are constructed. She says, "I'll tell you, it's been pretty rough these past few months. If it hadn't been for old Carlos here, I would have gone mad." Okay. So voltaic cell. You guys, in spontaneous oxidation reduction, you guys remember that involves remember oxidation, oil rig. Oxidation is loss of electrons. Reduction is gain, rig, RIG. We call it in short redox reactions. Electrons are transferred and energy is released. So you guys, in this case, what we're doing here is, and this is what this is showing, is taking a piece of zinc and you're putting it in a copper ion solution. You guys, copper ions always show a blue, and so if you have a blue solution, good indication copper ions are there. And so you guys can see what's happening here, right? You see the zinc is getting oxidized to zinc 2+, right? It's losing electrons and therefore its oxidation number becomes more positive. And in so doing, what happened to those electrons? Those electrons were transferred to the copper +2 ions. You guys see, and by gaining electrons, its oxidation right now, that's a 0. You guys see when it's pure elements, that's a 0, that's the oxidation number, and that was reduced. Well, unfortunately, with this, there's energy associated with the transfer of electrons, but in this case, the energy wasn't used for anything useful. The electrons were immediately transferred from the zinc to the copper plus ions, and so you guys see what's happening is, the zinc gets kind of used up, and then what you guys see forming here on the outside of the zinc is actually pure copper, as copper ions from solution are beginning to form in there. But that is energy that wasn't been able to be practically used. So what we do in a voltaic cell is, what we do is we separate, you guys remember we talked about balancing half reactions, we separate the oxidation reaction from the half reaction, and we cause those electrons to flow through an external source, and now we can use the flow of those electrons, which we call electricity, to power a device. So that's essentially what they're doing here. They're separating out the oxidation and the reduction. We can make that by getting the electrons to flow once again through an external device. And so what we're doing here is those electrons that are coming from the zinc, we're causing those electrons to flow through here. And this is a voltmeter, and it's showing this is, in a sense, constructing a battery that's generating or producing 1.10 volts. That's what we call a voltaic cell. So here's what it looks like, right? So we have our zinc, right? You guys remember it's being oxidized, so it's losing electrons. Now those electrons, because we've separated out the copper from there, the electrons are now traveling through, right, this wire. Those electrons are being, arriving here at this electrode, and you guys see what's happening is, those electrons are attracting the copper +2 ions. You can imagine the negative electrons attracting. And what happens is those copper +2 ions receive or gain those electrons and then form copper. So it says the oxidation occurs at the anode. So this is where oxidation occurs, right? The zinc's being oxidized. And then reduction is occurring at the cathode. You guys think about the anode and cathode. You guys know when you think about like a battery, think about on a battery, don't we have a positive and a negative electrode? That's like the anode and the cathode. Okay, that's what we just recognize as a positive. You guys know the little bump on a battery, that's the positive end, and the flat end is your negative end. Okay, and you guys, to help you guys remember where that occurs, this is how I always remembered it. Think about oxidation anode, they both begin with a vowel, O and A, and then think reduction cathode, those both begin with a consonant. So that's my way to remember, oh, oxidation occurs at the anode, and reduction occurs at what's called the cathode. Okay. So, you guys, look at what it's saying here. It says, once even one electron from the anode comes to the cathode, the charges in each beaker would not be balanced and the flow of electrons would stop. You guys think about it. What happens is, see, with the electrons coming to this electrode, right? Those electrons are going to be gained by the copper +2 ions. You guys see that electrons from here go to here, okay? So now, you think about it, if I had a solution here of copper nitrate, you guys see it's the positive and negative ions that kind of balance it out, so we have neutral solutions here. But now look, if the copper ions are gaining negative electrons and thus becoming pure copper, what's happening is we're pulling the copper ions out of solution. So you think about it, if positive copper ions are coming out of solution, what's that leaving behind? Only the negative nitrate ions. So then that would be making the solution negative. Now you guys think about it. Would electrons continue to flow to a negatively charged destination? that would not happen. So what you need is, because of that, basically what they're saying is this would not work just based on what we just described. What you need is what's called a salt bridge, a U-shaped tube that contains a salt solution to keep the charges balanced. So look at what we have. This is also what's necessary for a battery. Not only do you separate the oxidation half reaction from the reduction, but you also need a salt bridge. And that's basically a pathway that allows the ions to freely move back and forth between the solutions. So you guys think about it. As the positive ions are gaining electrons, positive ions are coming out of solution. Now this would make that solution negative if that's how you left it. Well, by providing a salt bridge, now you can have, for example, positive sodium ions from this solution coming here to stabilize the buildup, the negative ions here, thus keeping the solution neutral. So once again, you're going to have the positive ions come here, balancing out the negative ions that are still left, keeping this neutral, allowing electrons to flow. You think about on the flip side, the salt bridge works both ways. Think about when zinc's being oxidized, electrons are, right, as zinc loses electrons, what's it producing? Zinc ions. So those zinc ions are coming into solution. If we just left it like that, wouldn't you guys agree there would be a buildup of positively charged ions, because now we're getting more and more zinc positive 2 ions in this solution. So once again, we'd have a buildup of positive charge. Electrons would not be moving from a positive source. Remember, electrons are attracted to a positive source. So the salt bridge also allows negative ions from this solution to move here, which would stabilize the new production of the zinc 2+ ions. So basically you have positive and negative ions able to move back and forth via the salt bridge, keeping these solutions neutral, allowing for the electrons to continue to flow from the anode to the cathode. So you guys, once again, a salt bridge is essential to a properly functioning battery. So in the cell then, electrons leave the anode and flow through the wire to the cathode. And you guys see what will happen is, as the electrons leave the anode, the cations form dissolve into the solution in the anode. So that's what we talked about here. As the electrons reach the cathode, cations in the cathode are attracted to the now negative cathode. So right, we have the, remember that positive copper ions were attracted here. The electrons are taken by the cation, the neutral metal is deposited on the cathode. So the question is, what do you think you would see happen at each electrode? You know what you see. Over time, you know what? You would see this electrode kind of breaking down. It would become thinner and thinner, right? As zinc, pure zinc, which is what this is oxidized to the zinc 2+ ions which come out of solution. And now think about on the cathode end. So that was the anode end. On the cathode end, remember copper plus 2 ions that are in solution, they are gaining electrons and forming pure copper. You know what you'd have? You'd have a buildup of copper forming here. So you have this electrode becoming smaller, and you have this electrode becoming bigger. Then the question is, you guys, what do you guys think you guys know obviously batteries only last for a certain time. What's ultimately going to determine how long a battery lasts? What do you guys think? The battery electrons will keep flowing until what point? Well, just like in any chemical reaction will keep happening until at least one of your reactants is used up. So you know what? I would imagine this battery would just last until all the zinc has been oxidized and you have no more zinc, or until you used up all the copper plus 2 ions in this solution. All of them are used up, and therefore there's no more copper plus 2 ions to be reduced into copper. So ultimately, you guys see it's the amount of material that ultimately determines how long a battery is going to last. Okay. So you guys, we have this new term called electromotive force. Electro referring to electrons, motive obviously referring to movement. Remember, we've been talking about electron movement. And then a force. We're thinking about what's the force that's causing the electrons to move, okay? This is saying electrons only spontaneously flow one way in a redox reaction from higher to lower potential energy, right? They're likening it to water going from a place of higher potential energy to lower potential energy, water going downhill. The potential difference between the anode and cathode in the cell is called the electromotive force. So it's a force that's pulling the electrons, for example, from the zinc to the copper plus 2 ions. So basically we're looking at what is the difference in potential energy that causes those electrons to move. And the greater the difference, the greater the voltage, the greater the electromotive force, which, okay, we're going to talk about, is also called the cell potential. So that's called the cell potential And we designate cell potential as big E of the cell. So you're thinking like the potential energy of the cell. I'm thinking, what do you think you would more commonly call this? We don't really use that term electromotive force, which is really the difference in the potential energies between the substance that's being oxidized and that's being reduced. We know it as, starts with a V, I think you guys would know, that would be the voltage. So that's what voltage is the cell potential. So a volt is 1 joule per coulomb. A coulomb is a measure of charge, and we'll probably talk about that here shortly. So ultimately what we're going to do here in the next few minutes is show you how you can determine the voltage of a voltaic cell. So you guys are going to look, I believe I have this in your materials section in your Google Classroom. It's a list of the standard reduction potentials. Okay, I just want to make sure the video's still going. So you'll notice, look, it's all showing reduction. Notice, look, at all these are showing the electrons on the reactant side, indicating electrons are being gained by the corresponding substance, right? So these are all reduction potentials. It says for many electrodes have been measured and tabulated. So we're starting with the substances that have the greatest reduction potential all the way to the ones that have the lowest reduction potential, the ones that are not likely to be reduced, not likely to gain electrons. What you guys will notice is you got positive values and you got negative values. Positive values indicate that that's spontaneous, that that's going to occur. And hopefully, and you'll see what we use here, by definition, we're showing the reduction of H plus ions to form pure hydrogen gas. That we define as 0. So anything that's more likely to be reduced than the hydrogen plus ions will have a positive value. You guys see that? And anything that's less likely to be reduced than the hydrogen ions would have a negative value. And one thing I'm hoping you guys would notice is, if you notice about the ones that have positive values, if you notice, apart from the compounds, it gets a little confusing, but think about fluorine, oxygen, bromine, all these, oxygen, iodine. What do you guys notice? Aren't those all nonmetals on the right side of your periodic table? You guys remember what we remember from nonmetals? They have a tendency to gain electrons. Therefore, it's not surprising that they would have a positive reduction potential. And then look at the ones that have negative reduction potentials, indicating they're not likely to be reduced, not likely to gain electrons. Look at nickel, iron, zinc, aluminum, sodium. What are those guys? Aren't those all metals on the left side of the periodic table? Because you guys know, what do metals have a tendency to do? They have a tendency to lose electrons, not gain electrons. So we're going to show you guys how you can use these reduction potentials to ultimately calculate the voltage on a voltaic cell. Got the Muppets. Congratulations, it's a hand. They produced a hand. Okay. Standard. You guys remember what we used as our standard for 0, which we defined as a 0 voltage, is when hydrogen ions are reduced. And so basically that's what this is showing. The reduction potential for hydrogen is 0 volts. So basically when we say it's 0 voltage, notice it's not a positive reduction potential nor a negative. When we say 0, we're saying that this reaction here, it's not spontaneous in either direction. Right? We've got positive hydrogen ions gaining 2 electrons to form pure hydrogen gas. Notice it's called standard. It's the standard reduction potentials because we got standard conditions. We're going to have, it's going to be at 1 atmosphere for the gas, for example. And also your solution would have to be at 1 molar. Those are all standard conditions. So here's ultimately how you're going to calculate the cell potential, which is ultimately the voltage of your battery. To get the cell potential, you're going to get the oxidation potential, and you're going to add that to the reduction potential. You guys write this down. I've purpleized it. That's the equation you're going to use. You see, it's a pretty simple calculation. You're just going to add. So, for example, here's what we would do. So, think about, we wanted to calculate the cell potential for this reaction right here. Okay, and we're going to do under standard conditions. So, standard conditions means we have our solutions are going to be 1 molar. Okay, so if you look, so let's say we want to look up. Okay, so now look, we see the zinc's being oxidized. Now let's go back to our reduction potential. You guys are going to use your reduction potential chart. So I'm going to say, let's look for zinc. So I'm going to look at zinc, and You see how it's showing the reduction of the zinc ions. And you'll notice, look, the reduction, so when zinc ions gain electrons, they form pure zinc. And you notice it has a negative reduction potential. It's saying the likelihood of this happening, it's not spontaneous. It has a negative. That's what a negative reduction indicates. But now you guys look, in this reaction, it's the zinc that's being oxidized. So really, we don't have this reaction happening. We don't have zinc 2+ ions gaining electrons to form pure zinc. We have pure zinc losing electrons to form zinc 2+ ions. We actually have the reverse reaction happening. So you guys think about it. If this is the reduction potential, how do you guys think you would get the what's called the oxidation potential, which is actually the reverse reaction? Pretty easy, guys. What do you think you simply do? You simply change the sign. Because the negative, once again, indicates that this is not a spontaneous reaction. So if the forward reaction is not spontaneous, when you guys predict, isn't the reverse reaction spontaneous? And so the oxidation potential, what you do is simply change the sign. Okay, and so that's what they're doing here. So that's we're getting our oxidation potential. You guys remember it's oxidation plus reduction to get the cell potential. So remember it was a negative 0.76. So what do I simply do? I simply change the sign. Now you guys look, and now we're going to look at the copper ions being reduced. And once again, I just look back at my reduction potential chart, and we got the copper ions. And so you guys look at copper ions, and look, it's got a positive 0.34 is the reduction potential for copper ions being reduced. And in fact, that's exactly what's happening. Copper 2+ ions are gaining 2 electrons to form copper. So what's the reduction potential? It's positive 0.34. I don't change the sign because that is indeed being reduced. So then what do? Sorry guys, I always have to skip through all these. I have a positive 0.76, which was the opposite of what we saw in the reduction potential because the zinc was being oxidized. And then you guys, now this is the reduction potential. You remember what you do to get the overall cell potential? You simply add them together. You add those together, and so what is the cell potential of our voltaic cell? It's 1.10 volts. So that would be the voltage you would get based on using these materials. You guys think about that. That's something to bring up. You guys know some differences. Like here's your AA battery, here's your AAA battery. You guys have seen that. You guys think about what's the difference. Now, really, you guys, a lot of these batteries are made out of the same substances, especially if they were the same type, like if they're both Energizer or Duracell. Like, and you know what? This one, if you guys know, some of you guys might even know what the voltage is on a AA battery. They're all pretty standard. You guys will see it'll say 1.5 volts. Now, if you look at a AAA battery, you think about it, guys, if this is made out of the same substances as this, what would you guys expect the voltage of your AAA battery to be? It would be 1.5 volts as well. In fact, when you read it, it's 1.5. AA, AAAs, Ds, Cs, they're all 1.5 volts. So then you guys, somebody would ask, well, then what's the difference between a AA battery and a AAA battery? Obviously, you just look and you're like, oh, size. So ultimately, what's the effect? What's the difference? A AA battery simply has more of those whatever materials it has than the AAA battery. And so what's the result? It's simply going to last longer. So ones that would tend to be used, if you're going to put it in a device like, let's say, a remote control car that you're driving around, that you're going to utilize, it's going to utilize a lot of power, you'd probably want larger batteries. What do we typically use AAA batteries for? Like remote controls, right? Which doesn't use, that you're not going to use too consistently, and therefore it can, even though you have a small amount of materials. So once again, more materials, right? It's going to allow the reaction to continue for a lot longer, and therefore you're just going to last for a longer period of time. But what I want you guys to get from that is, what ultimately determines the voltage? It's not the amount of materials. That determines how long your battery will last. The voltage is determined by your choice of materials, what you're choosing to be oxidized and what you're choosing to be reduced. And the greater the difference between these, the greater the voltage. So that's what this is showing right here. You guys remember on a reduction potential chart, remember at the top was fluorine. In fact, fluorine, as you might expect, remember fluorine is our most electronegative element, and therefore it's not surprising it has the highest reduction potential. What we would also say about fluorine, it's our strongest oxidizing agent. Remember, the thing that gets reduced is the thing that's going to oxidize something else. Fluorine gets reduced because it gains electrons. Well, it had to get those electrons from something else. It's taking electrons from something else, so it's causing something else to be oxidized, right? So, and then you guys remember at the bottom of the chart, the thing that had the lowest reduction potential was lithium. What you guys remember, when it has the lowest reduction potential, what does that mean? lithium, you guys remember what lithium is? You guys remember alkali metals? Very metallic. They have a tendency to lose electrons, not gain electrons. So therefore, it has the lowest reduction potential, meaning it has the strongest tendency to be oxidized. And therefore, we would say lithium is a strong reducing agent. Its tendency to be oxidized, to lose electrons, it's going to cause something else in its presence to gain those electrons. We call it a strong reducing agent. Therefore, you guys think about it. If you wanted to make, you guys think about, what do you guys associate with batteries, especially when you're thinking about like, you think about whether it's your cell phone, laptop, or now electric cars, what kind of batteries are they using? I think you guys have probably heard, have you heard lithium batteries? What would be the whole thing about lithium? Well, you look on a reduction potential chart, it has the lowest reduction potential of all elements. Therefore, you think about by utilizing lithium, and then imagine you compare, or you combine lithium with fluorine, so you have like a lithium kind of fluoride kind of battery. You notice there's the biggest cell potential difference, and therefore what's going to be the result? You're going to produce a battery with a higher voltage. So the greater the difference in cell potential, the greater the voltage that's possible, right? The greater the electromotive force, the greater the force is pulling the electrons from the substance being oxidized to the substance being reduced. Okay, and that's what's saying, the greater the difference between the two, the greater the voltage of the cell. In this case, we took copper, which had a plus 0.34 cell potential, reduction potential, and a zinc, which had a negative 0.76 reduction potential. And then remember what we did? Since the zinc's being oxidized, we changed the sign, and then we add those together, and then the 1.1 volts was the result. Okay, as you guys should have probably recognized, that there would be some kind of relationship between the cell potential and Gibbs free energy. Okay, and this is showing the relationship. So if we want the Gibbs free energy, you guys remember what we use that for is to determine whether or not a reaction is spontaneous or not, whether or not it's going to happen, occur on its own. So delta G is dependent upon N. N is, I don't know if I show it here. Oh, you know what? I'm going to just go ahead and tell you before we derive. We're going to derive something here in a sec. So N is the number of moles of electrons. Okay. So for example, if we were doing this reaction here, notice zinc is losing 2 electrons, copper is gaining 2 electrons. So the amount of moles of electrons transferred is 2. So I'd put it 2 here. F is what's called Faraday's constant. So this is just a constant. You guys would write this down, have it in your notes. It's 96,485 coulombs. What that tells you is coulombs is a measure of charge. That's how much charge there is for every 1 mole of electrons. Okay. So we use the number of moles of electrons transferred, which we can see if we analyze the chemical equation. We use Faraday's constant and then multiply by the cell potential. Now you guys think about the relationship. If you guys ever if you calculate a cell potential, right? Remember when we calculated it for this, it was a positive. The cell potential was a positive 1.10 volts. That's how much volts we were going to get from these materials. Now think about it. So that was the cell potential. That's what I would put in for E. So that's a positive value times Faraday's constant, which is a positive value, times negative N. You can kind of look at it this way, or you can just look at it as this is a positive value times a positive value times a positive value is a positive value, and then what do? I change the sign. What kind of value for delta G are you going to get? A negative. You guys remember what a negative indicates? That there is a reduction in the free energy. Remember, that's called Gibbs free energy. Remember, that indicates a spontaneous reaction. Remember, things will ultimately go from the point of highest, or a point of higher free energy to ultimately to a point of lower free energy. And so negative indicates it's spontaneous, which is which you would imagine corresponds to the fact that you have a positive voltage. Let's say you guys are trying to predict whether or not a reaction would happen, okay? And you calculate the oxidative potential and the reduction potential, and you add those together, and let's say you get a negative 0.15 volts. You guys think about, what do you think the negative would tell you? That would tell you it's not going to happen. Electrons aren't going to move. You're not going to have that redox reaction occur. It's just not going to happen. And you guys see how this would show. Notice my cell potential is a negative, so that E is a negative. So now I have a negative times a positive is a negative, and then a negative times, you could however you want to do it. Negative times a positive is still a negative, but then what do? I change the sign. ultimately what's delta G? It's going to be positive. What do you guys remember from our previous unit? A positive delta G indicates a non-spontaneous reaction. So you guys should see that the E and the delta G in terms of signs correlate and kind of confirm one another. Okay, so you guys, we're going to derive one last equation. You guys remember the not means, it just means under standard conditions. So under standard conditions, when we have solutions, the solutions are 1 molar, and if we have gases, they're at 1 atmosphere. Okay. This was from the previous unit. I wouldn't worry too much. Notice I haven't put it in purple. You don't have to show the derivation. It's just when we arrive at our final equation, I want you guys to write it. We're just deriving it. This is just using a little bit of math. And ultimately, we end up with what's called the Nernst equation. You guys just write that down. This is in purple. So what this is allowing us to do is, this is telling you why when you would use the Nernst equation. This is also in your formula sheet on your Google Classroom. So what this will allow us to do is ultimately calculate the cell potential really for a voltaic cell under non-standard conditions. That's what it is. So to get the cell potential, I would get the standard cell potential. You guys remember how you get that? Remember, you just do add the oxidation and the reduction potential. You got minus this quantity R. R is a constant, 8.314 joules per mole Kelvin, times T. You guys should remember temperature should always be measured in Kelvin, divided by N, which was the number of moles of electrons transferred, and then divided by F, which is Faraday's constant, which we had on the previous slide. And then you'd multiply that by the natural log of Q. Okay? So you guys remember what we do? You remember what Q is? Q is set up the same way. You remember it's the ratio of products to reactants under conditions which might not be at equilibrium. You guys remember that, right? So just so you guys can see what we're talking about here. So for example, let's say, you guys remember, let's say we do a Q, right? You guys remember, right? Let's say we got reactants in a reversible reaction with products, okay? You guys remember how you get your Q? You get your concentration of your products over your concentration of your reactants, okay? So then let's say we are under standard conditions, okay? So let's say we're under standard conditions. You guys remember what standard conditions, when we're talking about solutions, they're all at 1 molar. So if the concentration of my products is 1 molar, and the concentration of my reactants is 1 molar, you guys, what's Q? 1 divided by 1 is 1. You guys, ln of 1, if you plug that in your calculator, put 1 and then you put natural log, you know what you're going to get? You're going to get 0. What's 0 times anything? That makes everything 0. So what's your cell potential? Your cell potential is equal to your standard cell potential, which is what you would expect if you had standard conditions in which your solutions were at 1 molar. So hopefully you guys can see that, you can see kind of how that works. But when you're in a situation where it's not under standard conditions, let's say your concentrations are not at 1 molar, now Q is not equal to 1, it's equal to something else, which ultimately, you know, affects this factor here, which is going to affect, it's going to have a slight effect on your standard cell potential, ultimately affecting your overall cell potential or your voltage for your battery. Okay. All right, last thing. Okay, I promise this is the last. I know it's been a lot. This is kind of strange if you think about it. I know it's kind of hard to see, but let's look at this one first. Okay, now look at how we set up this battery. Once again, right, we have our oxidation happening here at the anode. Electrons are being lost. Then they go to the cathode where the electrons are being gained. So what we have here are 2 nickel electrodes. Okay, we have 2 nickel electrodes, and we have nickel solutions. So you have these nickel ions in solution, right? So here the nickel ions can gain the electrons, right, where the reduction is happening, and then form nickel on here, and then the nickel electrode here is going to be eaten away as nickel is being oxidized. Now, this should not be surprising to you. You guys think about it. If I just took 2 nickel electrodes and I put them in 2 nickel solutions, would I expect electrons to flow? No. In fact, what this is showing is saying 0.0 volts. In fact, I wouldn't, you know, I just have the same exact substances on my oxidation as I do on my reduction. I wouldn't expect anything to happen. You guys, this kind of makes sense because look at what this is showing here. Now look at what we got here. Let's show a nickel being like here. Right here, we'd show nickel being oxidized. Here's the oxidation half reaction. Nickel's being oxidized. Well, here, we'll do the reduction first. I'm sorry. We'll do reduction first. Let's say the nickel plus 2 ions are being reduced, okay? So what would I do? I would look up on my reduction potential chart. You guys remember that chart? And we'll find that it's got a negative 0.25 volts. Once again, that's not surprising because you guys remember what we said. metals tend to be oxidized rather than reduced, so it's negative 0.25. But then on the other end, so that's the reduction end, on the other end, what's happening, pure nickel is being oxidized to the nickel 2+ ions. So here we're showing the reduction of nickel, here we're showing the oxidation of nickel. And you guys, right, when you just change the signs. And then how do we get the cell potential? You remember what you do? You take the oxidative potential plus the reduction potential, what's plus 0.25 plus minus 0.25, wouldn't that be 0? And that's a 0 voltage. Once again, shouldn't be surprising. But here's what's kind of interesting. Check this out. We have the same thing here as here. We still have just nickel and nickel. Notice this one was two totally different electrodes. Here, it's just nickel, nickel, and here as well, we also have a nickel plus 2 ion solution and a nickel plus 2 ion solution. What's the only difference? You guys notice how this looks darker than this? This nickel ion solution is 1 molar. This is 1.0 times 10 to the negative 3 molar. This is like a much lower concentration than that. Now check this, kind of strange. We use the exact same materials on both sides, yet we just have a difference in concentration. And you know what the result is? You actually get a voltage at I know it's hard to see, but 0.0888 volts. So we can actually get a voltage, and notice how we get it. Not by using different, you remember, we definitely would see if we got, you remember on the reduction potential sheet, we got, one that has a large cell potential difference. But in this case, we're using the exact same materials, just with a different concentration, and yet we still get an observable voltage. So how would that ultimately be calculated? Guys, look, so check it out. So you guys, in this case, right, let's say we want to get the cell potential of a voltaic cell under non-standard conditions. And we know it's non-standard conditions because both solutions weren't at 1 molar, right? So we use Nernst's equation, right? This is where it comes into play. So we're going to solve for E. So then, what is our standard cell potential? You guys remember? It's 0. You guys remember? We just add those together. This is what we get from our reduction potential chart, right? And then I'm going to go minus R. You guys see R is 8.314. You guys, I got kind of lazy. I didn't put the units because I didn't want to make it look more messier than it already looks. Times the T. Let's say this was at 25 degrees Celsius. Remember, you have to convert it to Kelvin, so 298. 273 plus 25 is 298. Divided by 2, you guys look, N, it's 2. Because when you guys agree, you guys look, 2 moles of electrons gained here, 2 moles of electrons gained here. How many moles of electrons were transferred? 2. So that's where the 2 comes from. And then you remember F is Faraday's constant. We plug that in. Okay, and then it's times ln of Q. Well, you guys, here's how we get Q. You guys see, here's the reaction happening, right? You got, think about it, you got nickel on the remember on that left side, it's being oxidized to nickel 2+ ions. And then on the right side, nickel plus 2 ions, we're gaining those electrons and thus being reduced. Well, if we look at the right side, you guys remember to get the Q, it's the concentration of the products over the concentration of the reactants.